So we have Geordie ready. Yeah. So going right into another incredible keynote speaker, we next have Geordie Rose, and I mean, Geordie is yet another really unique individual, and not many people have revolutionized one area of science and industry in their lifetime, and Geordie is now working on number two, right? So with D-Wave, Geordie basically created quantum computing as a viable in industry and as a serious engineering and business pursuit, and that's had a really transformative effect on the world, and it's sort of why quantum computing is a thing everyone's heard of now. And without giving that up, Geordie has now moved into an additional area of trying to build human-like AGI and human-like robots with his company Sanctuary. I've been lucky enough to visit their offices before COVID shut down the borders to Canada for a while. They're open again now. Fortunately, they've got some fascinating, learning robotic machines there, and their own very creative path toward AGI using these machines. So I'm very excited to hear what Geordie has to tell us about his approach with Sanctuary toward human-like AGI. So take it away, Geordie.
Thanks so much, Ben. Just a technical question. Can you guys see the video playing?
Yes, we can see you and we can see the video. It's all good. It's a
okay, excellent.
Embarrassment of riches.
Well, all right, excellent. Ben, thanks so much for inviting me to present here, and also for the very kind words. So I, like many of you, have become obsessed with this topic. I think, I've done quite a few things in my life, and I don't think that I've ever had the kind of.
Sorry to interrupt you. I think there are some Zoom screens overlaying your presentation. Could you please close? Yeah, that square one.
Oh, there we go.
Yes, thank you.
Is that good?
Yeah, there's one bar at the top, but I'm not sure if you can get rid of that one.
Is that a way to get rid of that one?
Unless you have it not on full screen.
Yeah, I am on full screen.
But that's okay. It's not this.
Whatever. I'll just leave it down here. There shouldn't be anything down there.
Yeah. Thank you.
Great. Yeah. So I've been. I came to here through a circuitous route, and Ben kind of talked a little bit about it. But I just wanted to give you some background on how I got to where I am, because I think it's important to understand kind of my perspective on the field, how I got to this point. So I started off in theoretical physics, and in particularly in studying quantum mechanics and the crossover between classical and quantum physics. And I wanted to say that I still think that theoretical physics is probably the best background for studying AGI there is. For a bunch of reasons that I'll get into. I guess this is more of a personal perspective than anything, but I found that a lot of the things that the way you think about the world when you learn about theory is a very valuable way to think about this problem. So anybody who's thinking about doing graduate work and is interested in AGI is kind of wondering about what to do, I would consider theoretical physics as one of the potential paths that you can take. So from that, I transitioned into trying to build a quantum computer. And I have to say that, if there's any evidence for the simulation hypothesis, being able to be in the front lines of building quantum computers is probably pretty strong evidence. The fact that I was even in a position to do this is just fills me with joy. This being at the front lines of new technology as it emerges is something that not a lot of people get to be involved in. And I was very lucky to be able to find a bunch of folks who had the same kinds of ideas that I did and make a go of it. And I was at D-Wave for about 15 years, eventually as the CTO. And after D-Wave, I joined a company that was working on something that was kind of what turned on the light bulb for me about the whole general intelligence picture, and this was Kindred. The founder of Kindred, I believe, is in the audience, Dr. Suzanne Gildert. So this was a shot at building a machine that had something like human-like cognition. A lot of the properties that Gary was talking about just now are remarkably relevant for robotics. You have to be able to sense the world. You have to be able to act sort of intelligently. You have to be able to understand things in a way that you might consider to be human-like, or at least all of those things help you build better robots. And during this journey, we accomplished quite a bit. We did more than 100 million grasps in the wild, where grasp is kind of this thing that I'm showing you here. And I think that the ideas behind how the team built this technology were on the right track towards building something like general intelligence. And another point that's important is that this made a lot of people rich. It made our customers rich, it made our investors rich, and I guess tactically important, it allowed Suzanne and myself and a few of the other folks from this effort the freedom to found Sanctuary with our own capital. So during the time at Kindred, I became more and more obsessed with this idea of building machines that had what you could think of as human-like or human-level cognition. Not really AGI, I guess, but something like it. And I'll talk a little bit about what I mean by that, because I think the definition here is important. But I saw this very clearly, this opportunity to be involved in something that was really of historic consequence. You know, you could argue maybe quantum computing is in that category, although I'm not entirely sure. But this is definitely in this category. I think it's very difficult to argue otherwise, that understanding the mechanisms of thought are potentially even of cosmic significance. If you believe that the type of cognition we have is unique or rare in the universe, it's ringing down through the eons, through our descendants into the universe is an activity that we can begin to participate in now. So it makes a lot of other human endeavors pale in comparison in terms of its potential significance, which I find irresistible. So everybody who is listening to this knows that this problem is crushingly hard. So it's hard in ways that I think language fails us when we try to describe how hard this problem is. So while I would like to be able to give you a prescriptive analysis of what I think we need to do, I can't. Well, what I can do is share with you some of the things that I've either learned or come to believe about kind of large scale structure of what solutions might look like, let's say. Where I'm going to start is that there is a clear analogy that you can draw. And of course, you know, analogies are not perfect, but they're useful, between the animals that surround us, including our fellow humans, and the machines that we call robots. So imagine a robot is a thing that moves around and does stuff and potentially benefits from having sensory input. So an animal like this wiener dog roughly acts like this. It has a bunch of senses, which are in the general sense, ways to understand or receive observations from the world around it. And then conditioned on those senses, it takes actions, and then those actions affect the real world, and that changes the senses, and this thing goes around in a loop. And anybody who's ever done reinforcement learning or anything like that is very familiar with this picture. It's kind of the fundamental ground rule of thinking about the world in terms of the RL worldview. But robots, of course, have the exact same problem. They're situated in the real world. They can have senses if we choose, and those senses can condition their actions again as if we choose. And then the actions affect the real world, and this thing goes around in a loop. And I found that one of the main frames upon which I always fall back to when I get confused about what intelligence and cognition and all these things are is to not so much think about the biological animal like the human brain or the human or the dog, but instead think about what would the constructed engineered analogy be? Because on the right-hand side, the robot we're the engineers. We have control over what the machine's characteristics are, what its cameras it uses are, and all of that. And it's often a lot easier to think about the world in this way than it is about this way, even though there is an analogy. And we're talking about physics. There's this thing called a pullback in differential geometry, where you can work in kind of one coordinate system and you can do stuff there and then map it back to a different coordinate system and hope that if your map is accurate enough, you can learn something about the other one, even though you didn't directly work in it. So this is one of the most important ways that I think about the problem. And by the way, the real world is very, very dangerous and unpredictable. And I think that thinking about the real world as a source of danger and unpredictability really cements why general intelligence, in the sense of being able to react to unforeseen circumstances quickly and quote unquote intelligently, is something that derives from this process of living in the real world. You can't exist in the real world and move around in it and succeed unless you can somehow deal with the unpredictability and danger that is inherent in it. Another point that I think it's important to make, or at least that colors the way I think about the problem, is that every single thing that has made it to this point in evolutionary history has had to deal with the real world in the exact same way that you do. Well, not exactly in the same way, but in the same general sense that they have a bunch of senses and they have to do stuff, and that doing stuff needs to lead to survival. And each end of this massively proliferating tree has an unbroken chain of successful reproductive events going all the way back to the beginning of life on Earth. So I think this is just more of a conditioning point to sort of understand how I and the team here think about this. But all of these things are worthy of an enormous amount of respect. They all have a property that we have trouble building in machines, and each of them is very different. So machines, of course, are not living creatures. They're very different in many ways, but there are some similarities. And Kevin Kelly and others have pointed this out, that in some ways you can think of the sum total of all of our technologies as being a little bit like a kingdom of life, maybe a seventh kingdom. And technologies are definitely a lot like species, but they have a property that other species typically don't, although some do, like cows. But most or nearly, well, I'll say all technologies have this very strong codependency with people. And the way I think about this is that unlike natural selection, which acts on living things through the usual mechanisms that we all understand and know, technology has a selection mechanism that has to do with human preference. So you might ask, why do certain technologies survive and others don't? And the answer is simple: people want them around. That's it. So there are lots of technologies that we used to use. By the way, I thought this might be extinct. Many of you may have never even seen one of these, depending on how old you are. It turns out they're not. People still sell these, which I found a little bit surprising, but there you go. But some of the things that we have around us have been extraordinarily successful, like the smartphones we all carry around and cars. So there's a very important question that I've thought about a lot, and that's about, it's maybe a fundamental question that often doesn't get asked by folks who are more interested in the science of something than the kind of the technology, I suppose, of it. And the question is, why would people want a machine like the sort that this conference is talking about? So you might say, why are you even asking that? It's so obvious, obviously. Well, I can tell you now, it is not at all obvious. I've spent half my life now talking to people about either using or investing in technologies like this. And I am here to tell you, it is not at all obvious that people want machines that have the properties that we're discussing now. And I would include basically all of the variants. Like we may have disagreements about what constitutes general intelligence or what flavor of it we might care to think about. Just like in the animal kingdom, you can imagine in the technium, there are untold millions of different kinds of thing we might consider general intelligence. So of all of those, are there any that people actually want? So here's 3 obvious examples. One of them is the statistics of language, the broken mirror held up to the Reddit posts. There's reinforcement learning in the digital world, and maybe more broadly than that. Here's another variant, which is some work by NVIDIA on building control systems for robots. Maybe this is something that you might consider to be generally intelligent or on its way. So no matter what you think about which branch of this technology spectrum you care to imagine is correlated with this thing that you really care about and have devoted your lives to building or thinking about, my view is that if you want it to actually come to pass, you have to imagine a parallel thing, which I'll call an economic driver, that is not the thing you want, but it generates and requires it. So let me go back to the quantum computing example. Quantum computers by themselves have no value. And that is very hard for a lot of people to understand. Is if I just build a machine and it is a quantum computer, the value of that thing in the sense of, a technology that will survive through time is 0. The value of the machine is what value it brings to people. Technologies are not independent from the people. People are the vectors of the procreation of the technology. You have to build something that people need or want. So in my language that I'm going to use, I'm going to call that an economic driver. So there's a very important point, maybe obvious, maybe not, that when you think about even something as so obviously valuable as general intelligence, it does not and cannot arise by itself. It needs to arise in tandem with the technology that evolves like every other technology, subject to selection pressure from people. So what is the economic driver for general intelligence? This is, I think, a core question, and it's a very hard one to answer. So I'm going to show you one potential way to think about this. Of course, it's not the only one, but it's the one that I've kind of put my weight behind. Right. So yeah, a question that has been asked several times, and Gary asked it too, is why don't we have this problem solved yet? And I think that the reason is that the economic drivers of general intelligence haven't been determined yet. So here's what I think. I think labor is the thing that's going to drive general intelligence into the world. And the reason is that there is an absolute critical lack of labor now in the world. And there are 2 kind of types of reason. One of them, which are the more powerful forces, are long-term acting forces that have to do with human demographics. Population birth rates have been below replacement in the Western world for 50 years. This is an amazing thing that I realized recently when I was studying some of these underlying things, is that people are not having children anymore in the Western world, or at least not enough to replace the numbers. And we don't see it yet in global population statistics because the less wealthy countries still have a lot more than replacement birth, but that number is plummeting also and will continue to plummet as technology picks up. We also have these short range forces that have to do with COVID and the disruption that's come from it, that have driven catastrophic numbers of unfilled positions in the labor market. If you read the news virtually every day, there's something about how people are not wanting to work under the conditions that historically have been the ones that were expected in terms of wages and the kinds of jobs that are done. And this number is huge. 10 million unfilled positions in the US alone. I mean, that's almost half of the workforce of Canada. It's a big number. So I'm going to show you one kind of robot that might be able to do some kinds of work. And this is what we call a general purpose robot, or at least that's the intent. Usually with robotic systems, the dogma is you build a robot to solve a particular problem. You specify a problem and you build something that is a solution to that problem. That's not this. Here, the optimization function, if you'd like, is fidelity to the human form. We wanted to try to build something that could do physically what people could do. And a lot of the problem with that comes from the hands. So robots are quite good at a lot of different kinds of things. Manual dexterity is not one of them. So usually robots are limited to what you can do with pinchers or suction cups on the end of their end effectors. Building human-like hands is a very difficult problem that we've kind of taken on head first. So at least on the robotics side of the projects that we've been working on, the hands are a significant portion of the problem. Now, of course, just building a robot that can kind of move around like a person is not enough. If you wanted to build an integrated system that could do work, and by which I mean nearly all work, the actual market for robots is tiny. The market for labor is enormous, and the difference is largely down to hands and cognition. So if you wanted to build a robot that could think like a person enough to be able to do work in kind of writ generally, you have to sort of think about this problem in stages, because obviously we don't have anything like the software, the control systems that would drive a robot like this yet. They're far too complex to be able to do this. So what do you do? Well, in autonomous driving, there was a clever thing done where there was a gradation scale between a person drives the car on the left and the car is just a dumb piece of plastic and metal, just responding to the agency of the person. And on the right, the car does everything. And there's a bunch of stuff in the middle. You don't go from one to the other. So for automating labor, and this is true for all robots, you can start from a perspective where there's a thing that I'm going to show you shortly, which is called analogous teleoperation, which is basically a person driving a robot just like you drive a car. And then there are a bunch of ways that you can increase the automation of the system all the way to a full automation system where you can imagine that the control system running in the robot is human-like in some way, or human-like enough to be able to do the kinds of work that we'd want robots to be able to do. So this idea is in a way that's analogous to autonomous driving is autonomous labor. So autonomous driving, we all know what that is or what it could be. Autonomous labor is just the analogous problem where you change the machine from a car to a robot, and the problem is not just driving, but being able to do work in a bunch of different contexts. So the control types that I'm largely going to be showing you, not all of them, but most of them, are of this sort. So when I say baseline level 0 autonomy, or the analogy of driving a car, this is what I'm talking about. So you have a robot, it's loaded up with whatever senses you can imagine putting on a robot, like vision, point clouds, audio, proprioception, touch, the whole business, just load it up with whatever you like. And you stream those senses over the internet or any network to a person, and the person receives the senses in an analogous way. So in this case, Suzanne's got a headset on that's receiving the visual feed from the cameras, potentially with some augmentations. And when she moves, those actions are transmitted in an analogous way to the robot. So part of the reason why you want a robot that kind of looks like a person like this is that it makes this kind of control simpler, because you don't have a hard problem of mapping degrees of freedom. It's just this person moves and the robot moves. If the person moves their head, the robot moves their head. It's basically a trivial control problem, just a one-to-one map. So this level 0 autonomy is very important. Like often I think there's a disdain for teleop that kind of lurks below the surface of a lot of roboticists and AGI folks. That is absolutely misplaced. I think you cannot get to where you want to go unless you can do this for a variety of reasons. The human mind is what I'll think of as a gold star controller for machines. There's never been a control system for a machine that's ever been built that's even remotely in the ballpark of what a person can do through a robot. So I'll just show you some examples of this kind of baseline control where remember, this is a person driving the robot. So far, there's no autonomy or anything. This is just a person moving a sophisticated robot around doing sophisticated tasks. So one of the things I'd kind of report on here is that this worked a lot better than we thought it would. So this is the 5th generation of this robot, and 5 generations of a complex machine is not a lot. You know, typically at D-Wave, we would do 7 revisions of everything before we'd even call it like a revision. This is just the 5th of the physical robot in the teleop system. And already it's doing things that you simply can't do with any other technology under teleop, of course. So it can manipulate small parts, rotate them. Everything here is in the wild. Obviously, you don't need to worry about lighting conditions or what you're dealing with or anything. If the system is physically capable of doing it, a person is going to be able to figure out how it's doing it. Every week, we do these kinds of tests, and I'll show you why in a minute. And every week, I'm kind of astounded by how capable this thing is under teleoperation. So here kind of is how we think about what it means to build something with general intelligence. And of course, there are lots of different ways to think about this. I'm not saying this is the right one or the only one or any of that. It's just the way that we think about it. We want to build a thing, a technological artifact that can physically and cognitively is able to do work, in the sense that I could take a regular person and plop them down, and I would have some expectations about what they would be able to do. I would want this robot to be able to do the same things. And that involves having conversations, it involves scene understanding, it involves reasoning, it involves goals, the whole lot. So this, of course, is kind of can be made fairly specific, but maybe at the cost of being very hard. I don't think there's a way around that. All of these formulations that we talk about are all very difficult to build. But here's what this one boils down to. It divides into two pieces. One of them is, can you build the robot itself? So that's the stuff, the atoms from which the machine is built, that is physically capable of doing work. And that is a very hard engineering problem. I would call it a grand challenge engineering problem. And then the second part is, can you build a software system that controls the body that you can't tell from a human pilot? So this is important. This is kind of how we position the problem that we're trying to solve, is that in the cases that I've showed you and some that I'll show you shortly, there's a person driving the robot. What we want to be able to do is build software systems that you can't tell are not people driving the robot. So you might flash to the Turing test. I suppose this is kind of related to that. But for work, we want to be able to have robots that can autonomously do work the same way that a human pilot would. And of course, this engages all of the problems that Gary was talking about and many more, because this is not just a problem about cognitive science and cognitive architectures, but it's also a problem about the physics and the engineering of robotic systems and how to get them to move the way that you want, which is by itself an entire field of human knowledge. I just wanted to point out that the far right hand of this kind of an analogy to autonomous driving is a very interesting endpoint. So if you can build a system that is completely autonomous and can do any work task that you ask it, that thing, regardless of kind of the words that we associate with it, is a very interesting thing that changes the world in all sorts of different ways. So there's a good question that you can ask about why is it that human-like cognition might be a target? And I'm asked this a lot more than you'd expect, because obviously there's lots of different ways to think about general intelligence or even narrow AI or technology at all. Why build this kind of technology? Why is this so important? And again, this is both trivially obvious and maybe kind of deep. So human-like cognition, of course, is not the best thing that you could imagine in terms of solving every problem there is, but it's got this peculiar feature that all of our ideas live inside of it. So if I'm Ilya and I dream up GPT-3, that was a human mind that did that, or a collection of them. And so, David Silver and Demis and the rest of those guys dreamt up all of this stuff. And the guys at NVIDIA, Nathan and others, dreamt up these control algorithms, and Suzanne at Kindred and now here is dreaming things up also. And I think that the reason why human-like cognition might be important from like a scientific perspective is that you imagine that if you do it right, the human mind can create an artifact that is kind of, let's say, deep enough to hold all of the ideas that we have about other ways to build AIs. So if this thing inside is a close enough replica of the thing outside, and we can put that into the world as being the brain of a robot or some other system, presumably that will have all of the necessary ingredients to be able to think about all of these other things as well. Whereas I don't think that's true for any of the other proposals that have been put forward. So anything that's like practically built or is being considered, it's very difficult to imagine that it would have the horsepower to be able to dream up all of these other things. And I think that even aside from that, there's a very human reason to build human-like cognition. It's basically everything we are, all of our dreams, emotions, memories, feelings, the way that we frame the world around us, why we think there's a tree over there when we look at it. All of that starts and ends within our minds. And I think that's a very fundamentally human thing to try to understand how that works. Okay, so lastly, I'm going to talk a little bit about how we go about this problem, not in any technical detail, but kind of give you a flavor for the approach that you need to follow when you build a control system for a robot. So the first thing is that there's a decision that we made to give the pilots and the AI the exact same data feeds in and out. So what that means is that the human pilot who is looking at the world or touching the world and then moving the world is using the exact same data channels as an autonomous agent would. So the AI doesn't get access to a whole bunch of stuff that the pilot doesn't, and vice versa. There's nothing that the pilot gets that the AI doesn't get, and vice versa. So there's an equivalence between these two control systems, exact same interface, and also critically the exact same job. We don't ask the AI to do something that a person can't do or you wouldn't expect a person to be able to do through this interface. So that's the first thing. The second thing is that we, for a variety of reasons that I'm sure all of you who've worked on robotics will appreciate, we need to be able to have a thing which we'll call a simulated robot in a simulated world. Just having physical robots and control systems isn't good enough for what we want. So I'm going to show you this. There's supposed to be audio that comes through. So if the audio doesn't come through, just let me know. So what I'm going to show you here is this is a physical robot. That's like a dude that lives in the real world. Back here is a simulated robot in a simulated world that's meant to be a one-to-one digital replica of this, not in the sense of being like what people usually call a digital twin, but an actual physical simulation, like with physics and all that. And the pilot here is going to move both in tandem. So this is just a mirroring exercise where the signals coming from the pilot get mirrored between the two. Okay, here goes. Let's pray for audio.
Okay, can you point at the yellow brick? Can you point at the orange brick? Can you point at the purple brick? Okay, can you push the yellow brick forward with one finger a little bit? Like away from you? Yep. Nice. It's good.
Okay, so cool stuff. The physical world and the simulated world are kind of in lockstep. So there's this is not perfect by any means, but I have to say that NVIDIA and Facebook and the rest of you guys who are working on all this metaverse stuff, thank you kindly. You're doing yeoman's work. These digital worlds are getting much, much, much better. And the robot simulations that you can make now are much more lifelike. And this is helping this kind of thing quite a bit.
Okay.
Now, just as an aside, you can do these local scale things where you've got like objects, and you can see in the back there that the digital world has the same kinds of objects, and you can imagine that the visual reactions to them are the same. So if the digital robot looks at these things, they'll actually see them and all of that. But you can also do cool stuff with much larger scale environments. So you could build a house, you could build a store. So for example, here's a store. You can imagine robots wheeling around inside these stores, interacting with things. So you can basically do a lot more than you could even kind of a year ago. The progress that's happened in these simulated environments is extraordinary. Now, of course, that's cool, but what we really want is a system that moves the robot. So everything I've showed you so far is piloted. So the way that we approach the problem is the standard, I suppose you could say, cognitive architecture, where you imagine the problem in its great majesty and horrible glory, and you try to divide it up into parts so that you can think about each of the parts separately, so you don't go crazy trying to think about the whole thing at once. And then you try to imagine who makes the best of these parts, and and to what extent they fit within the overall cognitive architecture. So I'll show you a couple. The reason I picked this motion planning one is I was just lurking on Twitter, and I noticed that Francois did a tweet, which I thought was kind of weird because, you know, he says he's looking for Riemannian geometry in TensorFlow, and it was exactly what he was looking for. And I was like, well, that's really weird for a couple of reasons. One, it's just inherently weird, but the other reason is that the way that do motion planning, which is the problem of how do you move a robot through the world when you kind of know where you want to go, which is task planning, uses very geometric ideas. So in this little video I'll show, the way to think about the motion is that the robot moves on geodesics in a very high dimensional space, which is essentially the joint space representation of the robot. So this robot has about 60 degrees of freedom. So imagine there's a 60 dimensional space and you have to move the robot through that. The motion is like a geometric geodesic. And you can imagine that this black thing is a repulsion surface. So the robot doesn't want to go there, but it does want to go where the red balls are. And also it wants to look at the ball that's on the that's over there. So this is derives from advanced ideas about using geometric approaches to motion planning that NVIDIA have pioneered. NVIDIA is really firing hot on a lot of the underlying AGI problems. I'm very impressed with both what they're doing and how. So we've borrowed some of these ideas, and by the way, it's not Riemannian geometry anymore. It's what's called Finsler geometry for reasons that I won't go into, but it's even more complicated to understand and figure out. But once you do, then you've got this powerful tool of not running into things you don't want to run into, and being able to move the robot towards the accomplishment of tasks, which you can think of as like places in 3 dimensions, 4 dimensions, I suppose, with time. Another thing I'd mention, because it ends up being an important part of what we do, and that's been mentioned a couple times already, is that we work with the psych folks, and they're great. And we've done our best to try to integrate what they're doing in terms of being able to understand that side of the world into this system, and have had quite a bit of luck doing it. So I just mention, if you're interested in hearing the latest update on Doug and what psych folks are up to, he did a Lex Friedman podcast recently, which was really good and highly recommended. All right, so getting near the last thing here is I'm going to just show you how we measure the AGI system. So on the right here is a way that is this thing is now not being controlled by a person, it's being controlled by the autonomous system that I just described. And the way that we test these things is both in simulation and in reality. Just to parse what's going on here. So this robot has a visual perspective that you can see over here. So it's looking down, sees a bunch of things, and Suzanne can ask the robot to do physical tasks or to answer questions about scene understanding or the affordance of objects, and all of these tests derive from a series of tests that were designed by economists to measure how fit for work a person is. So backing up a step, there's an entire field of science, I suppose, that is kind of related to psychometrics like IQ testing, where what you're testing is the ability of a person to do work, generally speaking, where the attempt is to reduce a person down to kind of atoms of work. Like, what are the sorts of things that you need to be able to do just work generally, not specific tasks, but any kinds of work. And so we adopted this metric, or at least created one from these tests, that resolves to a scalar. It's just a number. This number is a representation of a very high dimensional space, of course, so it's kind of a little bit weird, just like IQ is kind of a little bit weird. The things that it tests for is not really a number, but you can kind of boil it down to one if you squint. So what we do is we run all these tests and then we track progress. And the intent, or at least the the way that we hope this will proceed is that as you grow up this curve, you pass certain capabilities that these economists believe are required to do different kinds of work. So this physical system that I'm talking about needs to be able to do certain and be certain things in order to do work. It turns out that there's a very nonlinear relationship between those things and the amounts of work that you can do, which is kind of sensible if you think about it. Just basic human capability allows you to do an awful lot of different things in the economy. So as you climb this curve, you unlock different capabilities. And so instead of focusing on specific work tasks, although we do that too, we try to grow this number as kind of a measure of the progress against the goal. There are other things we measure as well, but I thought I'd point this one out because it's a very important type of thing. So I'm getting close to closing here. This is a couple more things I wanted to say. So the first one is that even though this problem is crushingly hard, and you guys know this more than most about how hard this problem is, I really do think that we're not so far away. Now, I know this has been said before. There's a long history of people thinking the problem was right around the corner. But I think that this time is different. And I think the reason is that we're already starting to see the signs of the sorts of things that we actually want already in the world. So the ability to physically manipulate objects, the ability to have sensor integration between, say, touch, proprioception, and vision and audio, the ability to hook in things where computers are obviously better, like chess, number theory, that sort of thing. They're already starting to work. So I think that there are maybe not machines just like us, like Data from Star Trek or something like that. Maybe that's not within reach, at least in the short term. But I think machines that are close enough so that you got to do a double take, or when you're having a conversation with it, you forget that it's not a person. That I think might be within reach within our lifetimes. And finally, I just wanted to close with a word about how I see the future. So I've been trying to work on things that would like really change the world my whole life. It's not always clear that technologies are for the good. We've talked a little bit about some of the potential downsides of social media and things of that sort. But I have to say, like, even though I'm not generally, I wouldn't call myself really fundamentally an optimistic person. I think I'm more of a realist. I actually think now my point of view on where we're headed has turned a corner. I think that we are looking at least in the sort of far future, like by which I mean, say 50 to 100 years, I think things are going to get a lot better. And partly, I think this is because this understanding how the human machine works is going to lead to a massive flourishing of awesomeness. So not only does understanding how our minds work unlock the ability to free people from the drudgery of work, but it gives us tremendous, and I think a kind of insight you can't get in any other way into how our minds actually work, which obviously is going to have a ton of positive implications. And if I was going to get really sci-fi, being able to build a machine that's kind of like a person might lead to being able to build like a machine that's kind of like a specific person. And that starts to look a little bit like side loading. We talked about Greg Egan before, but being able to build a cognition has some really fundamental implications about human society. And I think that even though it's very difficult to predict how the future will pan out, I am very optimistic about the directions that we're going and where we're eventually going to end once we pass through a period of turbulence between now and then. All right, thanks very much.